In Module 1, we first cover the basic concepts of integration. We start with the indefinite integral, which is the most general case. Then we go on to the definite integral, where we evaluate the integral over a specified interval. Just as is the case with differentiation, there are a number of rules that help us solving more difficult integration problems. We'll look at two of these. We start with integration by parts in Module 2. We'll consider integration by substitution in Module 3. These two methods can look similar initially, so it's useful to tackle them separately. In Module 4, we'll consider some economic applications of integration, namely finding consumer surplus and producer surplus. We finish up in Module 5 by looking at some special cases known as improper integrals. Integrals are improper if the limits of integration are infinite, or if the integrand becomes infinite at some point in the interval of integration. Integration is the inverse of differentiation, in a similar way that division is the inverse of multiplication. For this reason, the definite integral is also known as the antiderivative. We represent an indefinite integral in this manner. That is, we don't specify the interval of integration. Let's look at a simple example. So we have a function y equals 3x squared plus 5. Well, we know that the first derivative, dy dx, is equal to 6x. We'll let dy dx equal little fx. We can reverse the differentiation by taking the integral of f of x. However, we can't reverse the operation completely. If there's a constant in the original function, it's lost forever. It can't be recovered. We overcome this problem by substituting the constant of integration, c, for any lost constant. This is the indefinite integral. We integrate a function, and the answer is another function. We'll see shortly that in the case of the definite integral, when we integrate, we end up with a numerical value. Sometimes c can be determined. We might have more information about the function, or we might be able to make some assumption based on our economic knowledge. For example, remember that the marginal revenue function is the revenue derived from the sale of an extra unit of output. The marginal revenue function is the first derivative of total revenue, so we can integrate it to find the total revenue. We can safely assume that total revenue is 0 when there are no sales, that is, when Q equals 0. It's one of the I laws of business. On the other hand, if we have a marginal cost function, the solution's not so simple. We can integrate to recover the total variable costs, but unless we have additional information, we won't know the fixed costs. We've been talking about the indefinite integral. Here we have a formal definition. We can see the link between differentiation and integration. The integral of little f of x is defined in terms of the derivative of big F of x, plus, of course, the constant of integration. Another piece of jargon here, little f of x is called the integrand. Since integration is the inverse of differentiation, we can apply rules that undo differentiation. Most of these should be familiar from Lecture 4. We're just reversing the process. Firstly, the integral of constant is just kx plus c. This is the rule we apply most frequently. So the integral of x to the a, it's the reverse of the power rule in differentiation. What function do we differentiate to end up with x to the a? Well, the exponent of x would be a plus 1, and if we have a coefficient of 1, so 1 times x to the a, then the integral will have a coefficient of 1 on a plus 1. And so that's just the reverse of the power rule from differentiation, and you should be able to apply that quickly. That applies for any a except a equals minus 1. If the integrand is multiplied by a constant, we can take the constant outside the integral. We have a sum and difference rule. So if you have the sum of two functions in the integrand, or the difference of two functions, then we can separate the integral and make it simpler. If we have a summation sign, that's just a special case of the previous rule. Recall that the derivative of the log of x was 1 on x, so we can reverse that. Remember that the argument of a log is always positive, so we make sure of that by having the absolute value of x there. The integral of a simple exponential function shouldn't require too much explanation. Here's a rule that won't be familiar, because it's not the reverse of a rule we've come across before in differentiation, but it's one you should know. By the time you finish this lecture, you should be able to derive this rule. In fact, it's a tutorial question. Here we have the general rule for an exponential function. This is where the exponent is a simple function of x. Again, you should be able to apply that. And finally, we have an exponential function that's not to base e. Once more, this is just reversing the rule we had in differentiation. These are just the basic rules we need, so at this stage we can only solve fairly basic integration problems. Nevertheless, let's have a look at a couple of examples. Since we haven't yet come across any of the more advanced techniques in integration, what we can do in this example is to simplify the integrand and then apply the rules that we know. That's equal to, well, the integral of x on x cubed plus 3x squared on x cubed bracket dx. We can apply our addition rule and simplify, so that will be equal to the integral of 1 on x squared dx plus the integral of 3 on x dx. Let's simplify that further. So it's the integral of x minus 2 dx plus 3 times the integral, taking the constant outside, of x minus 1 dx. And now we're ready to apply what we might call the inverse power rule, equal to, well, we'll add 1 to the exponent, so it'll be minus 2 plus 1. That's minus 1, and we'll divide the coefficient by that new exponent, so it'll be minus 1, plus 3 times, we know that the integral of 1 on x is equal to the log of the absolute value of x, so L absolute value of x, and then plus c. So that's equal to, well, minus 1 on x plus 3 times log absolute value of x plus c. In example 2, we apply integration to a simple economic problem. We have a marginal revenue function, 100 minus 3q squared, and we want to determine total revenue and the demand function, more precisely the inverse demand function. Marginal revenue is equal to the first derivative of total revenue with respect to q. That's equal to 100 minus 3q squared. Total revenue then is the integral of marginal revenue dq. It's the integral of 100 minus 3q squared dq. We can simplify that. So we use our difference rule and take the constant outside the integral. Now we can apply our inverse power rules. So we've got a constant there, so that will be 100q minus 3 times, well, that will be q2 plus 1. That's equal to 3, so we'll divide by 3. And then plus c, equal to 100 q minus q cubed plus c. We know that total revenue is equal to price as a function of quantity times quantity. That implies that total revenue is equal to 0 when q equals 0. That means that implies that c is equal to 0. Therefore, total revenue is equal to 100q minus q cubed. We've been able to eliminate the constant of integration. As we saw before, total revenue is equal to price as a function of quantity times quantity. This is our inverse demand function. So price as a function of quantity, that's equal to inverse demand function, is equal to total revenue divided by quantity. So that's 100q minus q cubed on q, and it's equal to 100 minus q squared. So we found both the total revenue function and the inverse demand function. Now let's turn to definite integrals. We saw how the solution to an indefinite integral is a function. A definite integral has a numerical solution. In other words, the answer is a number. There's a strong link between the two. A definite integral is the limit of the sum of areas which are defined by the function found in the indefinite integral. If we graph a function, the definite integral is the area between the function and the x-axis over a specified interval. Well, there's a proviso there. That's the case if the function is in one quadrant between those bounds. We'll expand on that in a moment. But now let's see how the simple case works. Here we have a function, f of x. We want to find the area under the graph of that function between a and b. We can break up the area into rectangles. So here we have a rectangle. The width of each rectangle is delta x, and the length is defined by the function. So we'll have the height there is f of a, the value of the function at a. We can draw those rectangles. So the area under the curve between a and b is the sum of those rectangles. In this case, we have 6 rectangles. However, we can see that some rectangles are too small, here and here, and other rectangles are too big. We can make this measurement more precise by decreasing the width of each rectangle. We see up here that we have a much better approximation. So we can see as we increase the number of rectangles, in other words, decrease the width delta x, we get a better approximation of the area under the curve. I think you can see where this is going. If we increase the number of rectangles, so n approaches infinity, in other words, narrow delta x indefinitely, then the area A is the limit of the sum of those rectangles. We have that here. F of xi is the height of each rectangle, and delta x the width. So as delta x approaches 0, or n approaches infinity, we replace delta x with dx, and we replace the sigma sign with the integral sign. It's an elongated s. This is the notation suggested by Leibniz in 1675. The symbol is an elongated s, and it stands for the Latin word summa, meaning the sum of, or the total of. What sets this notation apart from the indefinite integral are the limits of integration. This notation was introduced by Joseph Fourier, another mathematician, in around 1819. So if we have limits there, it's a definite integral, and the answer will be a number. If there's no limits, it's an indefinite integral, and the answer is a function. We've defined the definite integral, but we haven't made a link between the integral and the derivative. Let's see how we do that in a slightly more formal way. Once again, we want to find the area under the graph of a function f of x. This time we begin by thinking about part of the area between a and b, area AT. T increases from a to b, and the area AT is a function of t. AT increases as t increases. Let's consider a small increase in t, delta t. So we're going from this t to t plus delta t. The increase in the area is delta a. The area under the function from a to t plus delta t is a of t plus delta t. So if we want to find the area delta a, that will be a of t plus delta t minus a of t. A of t is this area. Now the area delta a is between delta t times f of t, so here we have f of t and delta t there. So that rectangle, that's the left-hand side of the inequality. The right-hand side of the inequality is f of t plus delta t, so that height there, times delta t, this rectangle. So the true area delta a is somewhere between these two values. Given that inequality, we can divide through by delta t to get another inequality. Now let's take the limit as delta t approaches 0. This function here is just another form of the Newton quotient that we came across in lecture 4. So now we've found the first derivative of the area function, a of t. Not only that, we've shown that a prime t is equal to ft. How do we do that? Well, we have f of t here that's less than or equal to a prime t as delta t approaches 0. On the right hand side we have f of t plus delta t. Well, if delta t approaches 0, that disappears. So we have a prime t is greater than or equal to f of t, and it's also less than or equal to f of t. So it must equal f of t. So the derivative of the area function a of t is the value of the function f of t. It follows that the indefinite integral of f of t is equal to a of t. We use the t variable there as a dummy variable. Let's go back to using the x variable. So the area function a of x is equal to big F of x plus c. Big F of x is the integral of little f of x. The area over the interval a to b is thus a of b minus a of a. So we're substituting there b and a for x. We have the difference there. Of course the c's cancel out. We've got plus c and minus c. So the area over the interval ab is equal to f of b minus f of a. This is the result found by both Newton and Leibniz. It's so important, it's given the following name, the fundamental theorem of calculus. If a function little f is continuous on the interval ab, and big F is any antiderivative, that is the indefinite integral of little f, on that interval, then we have the following relationship. The definite integral of f of x from a to b is equal to f of b minus f of a. This is another way of expressing that. So it's f of x evaluated at b minus f of x evaluated at a. Some textbooks have that notation with the bar and the limits at the front. I think this one's the most common, and that's the one we'll use. Let's look at a couple of examples. We'll integrate the function 4 minus x squared over the interval 1 to 2. We'll see that's quite straightforward. However, if we integrate over the interval 1 to 3, we'll see that the problem's a little bit more complex. Why is that? Well, let's have a look at the integrand there. We have 4 minus x squared. That's a perfect square. We know that a squared minus b squared is equal to a minus b times a plus b. So 4 minus x squared is equal to 2 minus x times 2 plus x. So the roots of that quadratic are x equals minus 2 and x equals plus 2. That means our function cuts the x-axis at plus 2. That's between the upper and lower limit here for our second integration. Let's see how that works. There's our function. We see that it cuts the x-axis at plus 2 and minus 2. Big F of x is the integral of little f of x between 1 and 2. That's the blue shaded area. So we're integrating there. Just going through that in a little bit more detail. The integral of 4 minus x squared dx. Well, that will equal, we've got a constant there, so it'll be 4x minus, it'll be x to the 3, and we divide by 3 there. If it's an indefinite integral, we'd have plus c. We evaluate the integral. So that's equal to 4 times 2 minus 2 cubed on 3 minus 4 times 1 minus 1 cubed on 3. So we have the answer there, 5 on 3. That's the area under the graph, between 1 and 2. Now let's look at the case where we're integrating over the interval from 1 to 3. We see that for part of that interval, the function is above the x-axis, and for part it's below the x-axis. This is the wrong way of integrating in this case. We ignore the fact that the function cuts the x-axis, and we just plug in our values for 3 here, and for 1 there, and we get an answer there, minus 2/3. Basically what we've done is subtracted the green area from the pink area. That might be correct algebraically, but it's not correct numerically. We want the value for the total area between the curve and the x-axis. So we need to take into account the fact that the function cuts the x-axis. The correct way to approach this problem is to break up the function into 2 parts, taking the integral for the section above the x-axis, and then taking the integral for the section below the x-axis. And it's the sum of the absolute values of the integrals. So here's the correct way. We find that the function cuts the x-axis at 2. We saw we did that before. We solve for f of x equals 0. And then we split our integral up into two parts, first with limits from 1 to 2, and then from 2 to 3. We take the absolute value of the area below the x-axis. So this is the absolute value symbol. And then we proceed as before. The integral evaluated between 1 and 2, and the absolute value of the integral evaluated between 2 and 3. That gives us the correct answer, plus 4. Example 4 is just to illustrate that we need to be careful when we're integrating. In practice for this course, we'll stick to functions that are above the x-axis. For the simple reason that any function has an easy solution for f of x equals 0. It's probably a little bit too easy as an integration problem, and any integration problem that's challenging enough for us is probably a little bit too difficult to solve. A good guide for what to expect in this course are the tutorial questions. Let's finish up this module by looking at an economic example. A firm has a marginal cost function of 0.6q plus 2, where q is the number of units of output. Currently, it's producing 80 units of output. We want to work out the extra cost involved in producing an extra 20 units of output, so increasing to 100 units. Before we go on to the actual integration problem, let's review some of the economics behind this. Recall that marginal cost is the cost of one additional unit of output. So marginal cost is equal to 0.6q plus 2. So the marginal cost varies with the quantity, and that's equal to the first root of the total cost function, dTc dq. We want to find the change in total costs, delta total costs, when production goes from 80 to 100 units. That'll be total costs for 100 units minus the total cost for 80 units. Looking at that in terms of the marginal cost function, Q marginal cost of our marginal cost function there. We want to find the area under the curve. That'll be the change in total cost. That's also the change in total variable cost. Remember, total cost is total variable cost plus total fixed cost. It's the change in total variable costs because the total fixed costs are fixed. They don't change. Let's go on to the integration. Given our marginal cost function, that implies the change in total costs will be, well, the integral from 80 to 100 of our marginal costs, 0.6q plus 2 dq. Integrating that, we'll have 0.6 as the coefficient. That'll be q. A is 1, so the new coefficient will be 1 plus 1. We'll divide by a plus 1, 1 plus 1. Plus, well, 2 is a constant, so applying our constant rule, we'll have 2 times q. And we're evaluating that from 80 to 100. Simplifying that, we 0.3 times q squared plus 2q. We evaluate that function at 100 and then subtract the function evaluated at 80. So we'll have 0.3 times 100 squared plus 2 times 100, a big bracket around that, minus 0.3 times 80 squared plus 2 times 80, another bracket around that. Doing those calculations, we'll find that's 3,200 minus 2,080, and that's equal to 1,120. Put our conclusions then. Total costs increased by 1,120.